Wow, y'all, we're really here. Section number 8. Only three more sections, I guess, if you include the exam 3 review section, and then it's over. You guys are over the hump. You're over halfway. You've seen more than half the reactions. You're in it. So, couple of things. One, mid-semester meetings. I've made the calendar. I've imported all the grades in the spreadsheet and kind of looked at things. And I've sent out the signups to exactly no one. And so in the next day, I should have them sent out, probably by Wednesday night. Again, if you are one of my assigned section students, you will definitely be getting a link to sign up for a 15-minute meeting to chat. And also, if things are going worse than you anticipated, you can sign up for 2 slots and do a 30-minute meeting. But I am trying to meet with all of my students, which is about 30 total. And also for people who just come to section or my section or come to office hours or anything, or just want to touch base with me, it's open to anyone else as well. You just have to send me your email. So send me an email if you would like to sign up for that. Again, I'll probably send out sign-ups in the next week or so, and then I have slots open for meetings on kind of random days and times, so hopefully one will work out for you. Between tomorrow afternoon is the first meeting time, or sorry, no, Thursday is the first meeting time, and then it goes all the way through next Sunday. So I've kind of sprinkled them out. So we have that. Other things. I don't know. Let me say lecture 8. To be so honest, I don't love it. I don't love it because lecture 8 for E-17 was 2 entire lectures for the summer. 2 3-hour lectures that were kind of crammed into 1 3-hour lecture for the fall here. And in doing so, we also cut a lot of things. And so it's a very different way than I'm used to kind of approaching it, because also alkene land is very different than alcohols, ethers, epoxides land. And so I'm going to personally treat it for section as if we have 2 little mini lectures, and they are disjoint. Hence the importance of the transitions for today. With that also, we will see how kind of pacing goes, because again, it's new how to lay it all out. But I think that those are my kind of intro opening thoughts before we jump into things. Are there any kind of questions or ideas or musings or logistics, anything that anyone wants to bring to the table? I love the silence of a Zoom room. No one has anything. But it is actually great to see so many people here and attending live. Yeah, we have 9 whole people. Woot. Okay, cool. Well, in that case, kind of the overview, we are going to be doing the first 4 sections are this kind of alkene land, and then the last 3 will be alcohols, ethers, and epoxides land. Alkene land, this is a very tried and true path for organic chemistry. This alcohols, ether, epoxide is my least favorite unit topic in all of organic chemistry. It just feels very hodgepodgey, and it feels like there isn't really a good storyline. So I'll do my best with the material given. Without further ado, let's talk about alkenes and alkene land. So before we get into the actual reactions, I want to zoom out a little bit and talk about some terminology for alkene reactions. So all of these alkene addition reactions, what we are doing is we are adding things to an alkene. Instead of having a carbon-carbon double bond, we are going to create bonds to other things. And for each of the alkene reactions, there are essentially 3 big questions that you need to be asking yourself as you're studying it. So the simplified version of the 3 questions are what, where, and how. So first off, the what. So we are replacing our carbon-carbon double bond with bonds to 2 things. What are those 2 things? Each set of reaction conditions, you will need to know what are the 2 things being added to the alkene. Second question, where, is a question of regiochemistry, or what region or part of the molecule reacts. And this really has to do with something called Markovnikov's rule. Markovnikov's rule, I don't think that Serenia said this in so many words in lecture. She described it as like a mechanism that forms the most stable carbocation. I'm going to define it slightly differently. It's when you are adding two things to an alkene, Markovnikov's rule says the more electronegative group adds to the more substituted side of the alkene. So for example, a lot of the reactions add a hydrogen and some sort of nucleophile, and the nucleophile will be more electronegative than the hydrogen. So if we are looking at our alkene here, we have two sides of it. One side here is secondary. The other side is primary. And again, in terms of how many other carbons it's attached to, that's where I'm getting primary and secondary. So we would say that the secondary side is the more substituted side of the alkene, and this is the less substituted side of the alkene. So Markovnikov's rule says that if our nucleophile is the one that is more electronegative, it should add to the more substituted side of our alkene, whereas the hydrogen or less electronegative one will add to the less substituted side. And we call that the Markovnikov product. All of the reactions that we teach you in E-17 follow Markovnikov's rule and our Markovnikov product. So you shouldn't need to think about it or worry about it too much. But there are cases, especially in some of the halogen anti-additions, where Markovnikov's rule comes up. And so I wanted to kind of introduce this conceptually because we're going to be working with it a little bit. The alternative is, what if your more electronegative thing adds to the less substituted side of the alkene? This is called the anti-Markovnikov product. And again, it is not in E-17. But just want to set up the dichotomy in terms of the second question of where, which groups are added to which carbons in the alkene. Then, third question is how. How is a question about stereochemistry. When we are adding these two things to the alkene, are they going to be both adding on the same face, or are they going to add on opposite faces? So if the R groups are both added on wedges or both added on dashes like these, then we say that it is a syn addition. Now, syn additions here, you can see either both wedge, both dash, but also I think it's helpful to visualize, we have our alkene bond here. We know that we can interact with the top face of the alkene bond or the bottom face. And what that would look like just in terms of kind of arm choreography here is a syn addition is both up or both down. So this is syn addition. Now, on the other hand, what if one of your R groups adds on a wedge, one adds on a dash? That would be the equivalent of adding kind of up and down like this, which we call an anti-orientation. And so there's a little dance I like to do for the alkene additions, which is the stereochemistry options. We have syn, syn, anti, anti. It's dumb, but can we do it? 1, 2, ready, go. Syn, syn, anti, anti. One more time for good measure. Ready, and. Syn, syn, anti, anti. Wow, we love stereochemistry. Now, this syn and anti is going to be a property of the alkene reaction. So each reaction is going to specifically be syn or anti, or, secret third option, it's going to be mixed. You're going to get a mixture of syn and anti products. And so when you're going through and studying and memorizing these reactions, you need to remember, is the reaction syn, anti, or mixed? Now, all of this is a lot of detail. Like, suddenly we've zoomed in from like the what, which is very like smooth brain, to this of like, wow, the brain has pores. It's like so many curves. But this question of stereochemistry only matters if we make a stereocenter in our reaction. So look at this reaction, for example. If we started off with this alkene and we added two things, R1 and R2, well, these two are not stereocenters. So no matter if this reaction was syn or anti or mixed, we don't need to worry about wedges and dashes because there's no stereochemistry. There's no chirality to it. So we don't always have to consider this, but it is a property of each reaction that you are responsible for. The last kind of warning is, I know that this isn't really something for our class, but anti-Markovnikov. Just anti-Markovnikov is different than anti-addition. One's about regiochemistry, about which carbons things attach to, and the other one's about stereochemistry of things on dashes or wedges relative to each other. So that's my spiel on the kind of things that we need to be paying attention to as we go through each of these alkene additions. Are there any questions on these kind of terminology or big three questions before we jump into actual reactions? Okay. Well, then, in that case, I will go on to simple alkene additions. I won't play a transition because they're kind of related. So, I think one thing that's going to be helpful for y'all is to think about the alkene reactions as having different families. And the families are grouped together by mechanisms. So the first family here I call the acid additions. The acid additions, all of them take place in acid, and they all have a very, very, very similar mechanism, which is why we're kind of grouping them all together. So in the mechanism, the first step is the pi CC on your alkene is going to go and attack the sigma star H something. So if you are reacting with like HBr or HCl, it's the sigma star HBr, HCl. If you have like acid and alcohol, this would just be the protonated version of the alcohol here. But no matter what, you're grabbing a hydrogen in the first step. And when we grab the hydrogen, we essentially have two options, hypothetically, of which side the hydrogen could go on. It could either go on the less substituted side over here, or it could go on the more substituted side over here. And whichever side that the hydrogen does not add on is the side that gets a carbocation, because she used to have a bond, but now we have robbed her of the electrons. The electrons were shared, and now they are just in one bond on one side or the other. So the question of which one actually happens has to do with carbocation stability. So here we have a tertiary carbocation versus a primary carbocation. Which is more stable? Carbocation stability, throwback to SN1E1, hyperconjugation, the tertiary one, the more substituted carbocation, exactly. And so because we have one option is a tertiary carbocation and one option is a primary carbocation, we are just always going to form the tertiary carbocation. We are always forming the more stable carbocation. So after this first step where we add our hydrogen, we create the more stable carbocation, then at this point, whatever is left in our beaker is going to come and attack the carbocation, and then we will have the two things added. So for example, if this was HBr, then after this first step, we have a Br minus, and then the Br minus would come and attack the carbocation. So the two things we add are H and Br. Same thing for HCl, a Cl minus would come and attack. If we had like H3O plus here, then the thing that we would have over here is H2O. And I should really start the arrow from a lone pair on the oxygen here. And so then the two things that would be added were OH2 plus and hydrogen. And in the case of like alcohol or water attacking in this step, there might be a final deprotonation step. And that's just to make the products neutral. So the kind of overview for all the different things that we can make here is we can add, in all of these acid additions, we are adding a hydrogen and something else. And so we can make alkyl halides, either alkyl bromides or alkyl chlorides, by adding HBr or HCl. And then we can make alcohols and ethers by adding either H3O plus or alcohol with an H plus catalyst. Now notice in all of these, we are following Markovnikov's rule. So Markovnikov's rule says the more electronegative thing is added to the more substituted side. Well, bromine, chlorine, O, and O for both of these are going to be more electronegative than hydrogen. And we see that all of these are adding to the more substituted side of the alkene, the tertiary side. So it follows Markovnikov's rule. And then the question that we have to ask after the kind of what and the where is the stereochemistry. And honestly, I think the stereochemistry is the hardest part of the acid additions. So, first off, let's go and grab our hydrogen. That's the first step of the acid addition always. And in this case, we are always going to be forming the carbocation up top because this is a tertiary carbon, whereas this one down here is secondary. Remember, deuterium is just an isotope of hydrogen, and so think about it as behaving like a hydrogen on here. And so this carbon is only attached to 2 other carbons. We would say it's secondary. The reason why we sometimes like using deuterium for organic chemistry things is because it can help make stereocenters where there aren't stereocenters, just to illustrate points. So when we go and grab that hydrogen, imagine our alkenes here, our hydrogen can either add on the top face of the molecule, in which case it's added on a wedge, or it can add on the bottom face of the molecule, in which case it's added on a dash. Okay, so already in the first step, we are generating 2 possible scenarios here. And then when we have our carbocation, we know a carbocation is an empty p orbital. And with our empty p orbital, in the next step, the nucleophile could either attack from the top face or it could attack from the bottom face. So based on that, we have the versions where the nucleophile is added on a wedge if it attacks from the top face, or a dash if it attacks from the bottom face. And we have that for each of these options here. So in total, we are making 4 different stereoisomers as our product, 4 different diastereomers here. And we see that we get the syn options, where both of the things that we add are on wedges or dashes, and we get the anti options, where one's on a dash, one on a wedge. So we say that the anti-additions are not stereo-specific. They are going to form a mix of syn and anti. And they are a pain in the butt on tests to draw, because you have to make sure that you get all 4 of them. You can abbreviate them a little bit with a plus-minus notation. In order to do that, you would just draw 1 syn version, 1 anti version, and plus-minus, and then you don't have to draw all 4 structures, which is nice. But just make sure you don't make a mistake, and like, if you drew this is redundant. You are saying that you are drawing the wedge and dash version for both of them, and you only have the syns. So just make sure if you abbreviate it and draw only 2 structures with a plus-minus, that you draw 1 syn structure, 1 anti-structure. Cool. Any questions on the stereochemistry here before I have y'all try out a little practice? I say before I have y'all...
On I,
please.
sorry to interrupt,
No.
but I didn't have a question about stereo chemistry, but I did have a question about like just under the specific line reaction section.
Mm-hmm.
So when we have H3O plus that's going to like attack the alkene or is going to be attacked by the alkene,
Yeah.
it forms still OH on the more substituted side, and then H is not OH2O.
So what it looks like, the full mechanism is you have H3O plus, you deprotonate. Then over here, water goes and attacks, you have OH2 plus. And then you have one more final step where you just deprotonate the hydrogen on that.
Gotcha.
And that would make it into just the alcohol.
Okay, thank you. That makes sense.
Great. Cool. So I had said before I release a practice onto y'all, which normally in person I would like have y'all do it and I would go around to the groups. I can give y'all like 2 minutes to try it out on your own and then we talk through it. Do you want to do that, or do you want me to just straight up talk through it for this exercise number 1? Maybe I'll explain what it is while you vote in the chat if you want 2 minutes to try it on your own versus if you want to do it together. The exercise is, I put 2 reactions here and I want you to draw the possible products. And this question's really going to get at how many products are formed. And so we need to be thinking about that stereochemistry a lot. I see 2 votes for trying out on your own. Okay, amazing. 3 votes. So I'm going to give you 2 minutes. Try it out. hate to say that's been 2 minutes. I know no one is done. I know that. But I like that you've started to think about it. Let's try to put it together. So immediately when we see an alkene reaction, we should be thinking about how do we answer those three questions. So we know with H3O plus, we add OH and H, it's Markovnikov, and it's mixed. HCl, we know we had an H and a Cl, we know it's Markovnikov and mixed for stereochemistry. And then my rule of thumb is even if you are just trying to get the products, whenever there's a carbocation in the mechanism, I think it's always worthwhile to draw the carbocation intermediate. Because the thing is, there is a conceptual reasoning to make sure that you are placing the carbocation in the right place that needs to be done. And sometimes when we're trying to do our fake mechanism, just draw the product, skipping over the carbocation step will lead to mistakes. And so, yes, I love thinking just at the line reaction level and not doing full mechanisms if we don't need to. But for carbocations, let's draw the intermediate. So, in both of these, we have a tertiary carbon versus secondary carbon. And so we are going to be forming the tertiary carbocation in both cases. Now, in this left molecule over here, we see that there is already a hydrogen on the less substituted side. So then in the first step, when we add another hydrogen, we see this carbon is not a stereocenter. Lovely. We love when there is not a stereocenter. It makes our lives easier. But over here on this one, on the secondary carbon, there's a deuterium. And so it matters whether our hydrogen interacts and adds on that top face or whether it adds on the bottom face. And so we are going to have a version where the hydrogen adds on the top face on a wedge and the deuterium's pushed down on a dash, and vice versa over here. Okay. So now that we have these options, we know with a carbocation, we can attack from either the top or the bottom face of the MTP orbital. And so what we get for our products here, we get the version where OH is added on a wedge, and we get the enantiomer, the version where the OH is added on a dash. And so we get two products out because it could attack from the top or the bottom face. And then over here, I just didn't draw the hydrogen because we don't have to. We can imply that for skeletal structures. Then on this other molecule over here, we get two stereocenters that are formed. So we are going to get the version here where our hydrogen and our chlorine both add on dashes, and we're going to get the enantiomer of it where they both add on wedges. So the plus minus here is going to give us the flipped version of both of these stereocenters. But then we also have to draw this second structure. We are going to get the version where the hydrogen is added on a wedge, and then the chlorine would be added on a dash. So the hydrogen and chlorine here are anti to each other. And then we are going to get the enantiomer of this, where the hydrogen's on a dash and the chlorine's on the wedge. And so the important part when you are doing this, when you're forming a lot of diastereomers for your product, is you need to make sure whatever two things you're adding, you draw a syn version, and you draw an anti version, and include the plus minuses. Alternatively, you can draw all four structures if your time is less precious. So, question. We randomly assigned another thing attached to the carbon as dash or wedge. So, it's kind of like here, when we have our like alkene here, this is planar, trigonal planar. And so, if we are flat and planar, and our hydrogen adds on the top, suddenly it becomes the wedge. It is the thing coming out of the page. And so something else has to be pushed as we go from trigonal planar to tetrahedral. And so yes, you just choose one of them to be the dash. And typically you choose whichever is going to be easiest to write. Yeah. And then it doesn't matter which, nope, it does not matter which of the ones you assign as the dash or wedge. Just make sure you're consistent when you're drawing all your products out. Cool. So that's kind of the intricacies here for acid additions. Without further ado, let's talk about the next family. So acid additions is the first kind of cluster of like 4 reactions. And the next cluster of reactions are called the halogen antiadditions. So all of these take place with either a Br2 or Cl2, or they can also happen with an I2. It's just I didn't have space to write all of them, and also the iodine ones are like less common. Um, but all of them are going to add halogens, and they all are kind of riffs on the same core mechanism. So let's look at the core mechanism, then we'll kind of see how we can riff on it. So we start off by interacting with the dihalide. So imagine we have like Br, Br. And the mechanism here is this interesting concerted mechanism. So the pi CC is going to go and attack an acceptor orbital on Br2. So in this case, it's going to be the sigma star Br, Br, halogen, halogen. But then at the same time as that is happening, a lone pair on the halogen is going to go back around and attack the pi star CC. And so this kind of struggle that happens of you attack me, I attack you, feels very Shakespearean. It's Tybalt and Mercutio. You attack me? No, I'm going to attack you. And it kind of drives itself in a circle. This third arrow is just kind of a consequence, because we know if we place electrons in an antibond, so here the halide antibond, the bond has to break. And so as a consequence, we are going to be breaking this bond as well. So after this first step, the concerted step, and notice how this is a much different first step from just the protonation with the acid additions, what we form is something called a cyclic bromonium or cyclic chloronium ion, depending on if we have a Br or a Cl. So this is a 3-membered ring with one of these halides, and we know our halides normally like to have 1 bond, 3 lone pairs, but now they are forced to have 2 bonds. They have to share more of their electrons than they would like, and so they have a positive formal charge. This 3-membered cyclic bromonium chloronium ion is super, super reactive. And from here, what's going to happen is a nucleophile is going to come around and attack on the more substituted side and break open this ring. Now, the exact reason why, like, we have a couple of like specific things that happen. So one, our nucleophile is always going to attack on the more substituted side as part of Markovnikov's rule. And the second thing that happens is it is always going to be attacking from the bottom. So looking at our products here, our nucleophile, when it's added, when I say add from the bottom, it's going to add from whichever side our cyclic bromonium or chloronium ion was on. So remember, in our first step, we are having our alkene, and then we are forming a 3-membered ring. That 3-membered ring can be up, or it can be down. And so we can form the wedge version and the dash version. But then we have to think about, okay, well, if we are forming the wedge version, where they're both coming up, where are the antibonding orbitals? Well, we know the bonding orbital is right here, so the antibonding orbital is along that axis. And so you have the larger lobe here on carbon, the less electronegative side, smaller lobe on bromine. And so if our cyclic bromonium ion was on a wedge, like this, we know that our nucleophile, when it comes and attacks, if it's attacking the antibonding orbital, it has to attack from below. So the wedge intermediate, our nucleophile adds from below. And then the halide from this 3-membered ring is still on there, and it's on the wedge for the less substituted carbon. So this is the kind of anti-stereochemistry of these reactions. I call these the halogen anti-additions because this anti-stereochemistry is so crucial to the mechanism. You are always going to get, if your halogen's on a wedge, your nucleophile is going to be on a dash, and vice versa. Over here, we have the cyclic bromonium or chloronium ion going down, and so the antibonds are going to be above the ring. And so the nucleophile attacks from the top face, and it's on a wedge. So no matter what, the two things that you add are always going to be anti to each other. You are never going to get syn for these mechanisms. The other part of it, the other question I said, is the nucleophile always attacks the more substituted side. And thinking about this, when we have a positive charge on bromine, it essentially makes it really electronegative. So a carbon-bromine bond is already polarized, and a formal charge on it makes it really, really polarized. And so we have partial positives on both of these carbons. And so what we can start to think about then is which of these partial positives is more stable, kind of like which of the carbocations is more stable. And here, a tertiary partial positive is going to be more stable than a secondary partial positive. And so, because this is the most stable partial positive, it is the one that is the most extreme polarization of the bond, and it's the easiest one for the nucleophile to go and attack. So that is why we are always going to be attacking this more substituted side. And then this anti-bonding orbital placement is why our stereochemistry is always anti. Ooh, I think I threw like a lot of like theory at you all at once. For a two-step mechanism, there feels like there's a lot going on. And that's kind of the challenge of these. Dahlia, sorry.
Yeah, I don't understand how there's a partial positive when it is positive. Wouldn't it be a partial negative?
So I hear where you're coming from, but think about it. Uh, how do I put it? Formal charge really is kind of like a bookkeeping, and you can have formal charges that don't actually match up with charge distribution in a molecule. So, like, you're right, like, relative to this bromine, this carbon has more electrons on it. But think about, like, sharing of electrons in a bond. A carbon-bromine bond, the bromine is more electronegative, so there's going to be a partial minus and partial plus polarization in the bond that is separate from formal charge. And so it's those kind of notions of formal charge as like bookkeeping, and then like polarizability and polarization and actual charge distribution. They're very connected, but they are a little bit different from each other. What the positive formal charge on the bromine does is essentially makes it even hungrier for electrons. So in this polarized bond where it's already pulling a lot of electrons away from the carbon, it's going to pull even harder, making the partial positive on carbon felt even more. Another way to think about it is if there's a deficiency of electrons in one part of the molecule, it affects the whole region. The whole molecule is going to be adjusting to try to get electrons towards the deficiency of electrons. But yeah, it's kind of weird to think about that way. Yes, so kind of what I'm getting at here, with a lot of moving pieces and a lot of theory behind this, the challenge of these kind of set of reactions, really for both lecture 7 and lecture 8 here, it's not that they're going to be super long, like some of the CAD reactions or some of the carbonyl additions like acetal formation. These are going to be short reactions. They're only going to be typically like 1 or 2 steps, maybe 3. But then you're really going to be having to think about these questions of stereochemistry and regiochemistry, and that's where the kind of challenge comes in. In a traditional organic chemistry class, alkene reactions are actually the first reactions that are taught. So at like most state schools, this is the first set of reactions, and then they don't get to carbonyls until OChem 2. But I don't know. Carbonyls I actually think are easier than this because you have to think through so many things. So if we just have like Cl2 or Br2, then what is our nucleophile? Well, if we had like BR, we kicked off a Br, the thing that's our nucleophile is a Br minus. And so the things that we add are 2 bromines, and they are added with an anti-orientation to each other. If we had Cl2, we add 2 chlorines. Now, the technical name for this functional group is, it's called a vicinal dibromide. Think vicinal in the same vicinity, so they are like neighbors to each other. Dibromide, there are 2 bromines. But we can see that if we add a solvent to this reaction, the products change pretty substantially. So imagine that we did the same reaction, Br2, but now we have an H2O solvent. So the first step is the same, we form our cyclic bromonium. But now, who do you think is going to be the nucleophile that goes and attacks? One of the billions, trillions of water molecules, or one bromo boy? Like, it's just kind of a numbers game. Like, the H2O is much more abundant, and so it's going to be more readily able to attack, or like more likely to attack. The other thing is like, this is going to be an ion that is created in water, and so there's going to have like a hydration shell around it with like the partial positive hydrogens kind of solvating this. So because of that, whatever our solvent is, if we have a solvent, is going to be the thing that comes and attacks. So we would get, after this intermediate, the bromine on the bottom is still in a wedge, and the OH2, it needs to attack from the opposite side of our ring structure. So our ring was on a wedge, So our OH2 needs to add on a dash. That would force the methyl that's on there to be on the wedge now. And it's kind of like pay attention to where the nucleophile is going, and then it's going to shift everything else. We kind of saw that when we were drawing the stereochemistry and creation of a stereocenter in the last problem. But it kind of just pushes everything up when it attacks from the bottom. So then we are so close to the end, but we are charged, and we know that our final products are rarely charged. And so we're just going to have one more step, which is a deprotonation step. And then that's going to take it to the product where we've added an OH and a Br. He's just one bro. He is. So when we add OH and Br, so when water is our solvent, the thing that's formed is called a halo for halogen, hydrogen for water, or OH. So a halohydrin. And we can do this with chlorine as well. And the exact same thing happens with an alcohol as the solvent. We would have HOR attack, and then we would do a final deprotonation after that. And the thing we've added is an OR. So technically what we've created right here is an ether, and next door we have a halogen, so we call it a haloether. Now these names might seem kind of like roll my eyes, again, we keep making things up. Again, I think it's helpful just to have a name and to have words to describe it, because otherwise you're just like, yes, it forms the thing. But we are never going to test you on halohydrogen, haloether, vicinal dibromide, all of that. But that is the core idea for the halogen antiadditions. Questions on her?
I have a question, Colton.
Yeah.
Up above in the general mechanism section, I know you said that the nucleophile will attack the more substituted side, and you also said, I think, that it adds onto the same side that the ion was on.
The opposite side that the ion
And
was on.
the opposite side. Okay, cool. Yeah, I bet that clears it up for sure.
Cool. So, for some practice on this, one of them is the official section problems, and the other one is from the practice that I think is a good starter one. So, this is going to be a halogen antiaddition, but we have a mixed dihalide. Ooh, very interesting. So, what we need to think about is we know our first step is going to be I attack you, you attack me, and then we kick off a halide. But which side are we going to attack? Are we going to attack the iodine side, or are we going to attack the chlorine side? And one note is that chlorine is more electronegative than iodine. So, given this fact, can you take a minute to vote in the chat? Who are we attacking? And let me see if I have voting music. Yeah, I do. I have voting music, so vote in the chat. Do we attack iodine or chlorine? Is it coming through at all? It's the Jeopardy theme. Okay. Ba-da-bum, ba-dum, bum, 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 bum. Cool. There are enough votes that I will stop doing that. So remember, our antibonding orbital is going to be larger on the less electronegative atom. So here, iodine is the one that's more electronegative, less electronegative. Chlorine's more electronegative. And so we are just going to have a larger antibonding orbital over here for the iodine. And so that is the side that our alkene is going to go and attack. So our alkene attacks iodine. And we know that as a consequence of that, it breaks this bond. Our pi CC is attacking our sigma star ICL. Then, at the same time, if you attack me, I attack you, the lone pair on the iodine is going to come back and it's going to attack the pi star CC. So a lone pair on iodine is attacking the pi star CC, which in turn breaks the pi bond, but we see the electrons in the pi bond are already going to go and grab something. So great. Evan, what's your question?
Can you talk a little bit more about what it means that it will attack the less electronegative side? Because wouldn't that imply that, like, in our solvent situation, it would want to attack the less electronegative thing, which would be the solvent and not the nucleophile? But that's not what happens, right? Is there a reason
So
that
again,
that
I think that
happens?
it's a mixing up of electronegativity and uh, charge arguments with like formal charge. Like when we are talking about which side do we attack here, these are both carbons. They have the same electronegativities. And so it's not going to be a different sized antibonding orbital between our two options of which we attack here because they're both carbons. And so we have to base our decision on something else, in which case we do the partial positive charge stabilization and all of that. But here, there is a legitimate size difference between the orbital as our target on the antibonding side for the iodine versus the one on the chlorine. And so it's a larger target. Again, the ideas are kind of overlapping here. The other thing that you can think about is if chlorine is more electronegative, this is more partial negative, this is partial positive, we are attacking the partial positive side, the electron deficient side. So like they both are there and overlapping, but I think that it's that kind of like collage of them that makes it a little bit trickier. Yeah. Cool. So when we do this, let's see what we get. We are going to make a cyclic iodonium ion. Wow. Don't we love to know that that exists? And we're going to get the version where it's added on wedges. And also, we are going to get the version where it's added on dash. So I'm going to put plus minus. But plot twist, question. Do we have any stereocenters? She has 2 hydrogens. She has 2 methyls. No stereocenters. So actually, we don't even need to do that. We could draw straight lines, and that would be 100% correct and would be including stereochemistry because there is no stereochemistry. There are no stereocenters. So, hey, it doesn't even matter. Then in our step 2, the chlorine's going to come along. And remember, it is going to attack the more substituted side. So we know that it's going to come along and it's going to attack on the side that has the 2 methyls on it. So our final product that we get out of this is kind of our carbon backbone that we had. The top carbon's still going to be connected to iodine, and the bottom carbon's now going to be connected to chlorine. Again, we do not have any stereocenters, so we do not need to account for stereochemistry. Or I guess we have accounted for stereochemistry because there are no stereocenters. So it just makes our lives easier. Yeah. If there was stereochemistry, like if one of these was an ethyl or something, then we would have to form the enantiomers and make sure to keep careful track of that and make sure that we formed them on anti-stereochemistry. So this is kind of the easier one. This one's from the practice problems. And this one's from the section handout. So in our section handout version, we have something that looks a little bit complicated. And maybe why don't I draw what the initial expected product might be. We might expect it to look something like this, right? Having bromines on each carbon here in our alkane. We're just adding Br2, we don't have a solvent. But if we look at our initial molecule, something that seems kind of problematic is we have this boy over here. And this is an alcohol. So, with this alcohol present, we might need to be thinking about the version that looks like Br2 and ROH, like what that mechanism looks like. So let's kind of start off the mechanism and then see where we might take that into effect. So our first step with attacking the halide, you attack me, I attack you, and we have a consequence arrow. That makes us look like this. And the nice thing, again, is, or actually, in this case, do we form any stereocenters? So I'm going to draw it without stereochemistry first. Well, this one over here, 2 hydrogens, not a stereocenter. But this one with the methyl, that is a stereocenter. So we do need to keep track of that. So why don't I just make the bromine on a wedge, and then I'll make the methyl on a dash. And that would be the bromine kind of interacting with the top face and making kind of an upward triangle. It could also add it at the bottom face and made a downward triangle. Both are options. So, because both are options, I'm going to put a plus minus here to say, hey, we could have formed the cyclopropylium on wedges, or we could have formed it on dashes. So now, we've kicked off a Br minus, but the Br minus is here, and then we have an alcohol that's also present, and it's on the same molecule. So here, the argument's not really the same argument that we had from solvents. Solvents, we had like a numeric, like it will outnumber argument. But really, that argument was kind of kinetic. It was like, whatever can get there the fastest is going to be the thing that attacks. And so, when one bromine was outnumbered by bunches of waters, the water wins. But here we have one bromine versus one alcohol here. And then who is faster? Well, one of them is an intermolecular reaction between two separate molecules where they would have to bump into each other in a very specific way, and like they are in different parts of space and they have to bump into each other. Versus here, this molecule, this intramolecular attack, could just happen from like the molecule like wiggling around and it just kind of like bumps into itself. And again, it's the thing of that sounds kind of unlikely when I phrase it that way, but it's more likely than this bromine that's exploring the other side of the room. So what we're going to have here is our alcohol is going to go and attack instead of the bromine, just like our version when we are an alcohol solvent. And we are going to attack the more substituted side. So we attack that carbon that's more substituted, and then we kick out the bromine. Okay, so now let's be careful about this. We know our bromine was on a wedge. So that means our hydrogen, or our OH, needs to add from below, from the dash. So it's going to look a little bit weird. There are a few different ways to draw it. But let me try drawing it this way. So I'm going to do, this is a 1, 2, 3, 4, 5-membered ring. And I know an oxygen's in it. And then I will make this carbon 1, 2, 3, 4, 5. But we know that the oxygen's going to be attacking from below. And so what I'm going to do is I'm going to put this on a dash within the ring. I know that feels kind of weird, right? Like I see some scowls. Yeah, it's ugly. It's bad. But let's trace it and see what happens. Well, this lets us keep the carbon and the bromine that were originally on here still in the plane of the page, and we knock this methyl that was on a dash originally now up on a wedge for that stereocenter. So to be clear, I do not like it. Same I am. We also are going to have the enantiomer version of this. But a lot of this, like this whole kind of tracing thing, it's really just to help us be careful about our stereocenters. Because if we look at this, we see actually this top carbon, that's not a stereocenter. And we see that this one is a stereocenter. And so as long as we know we are going to form both versions of our stereocenter, we can draw it any way that pleases us. So another equivalent way of drawing this would be keep everything in the plane in the molecule, and then draw the dash and Br and the wedge methyl, and we have a plus minus this way. These are communicating the same thing. Basically, it's communicating that we have a stereocenter here, and the plus minus says that we're going to get both versions. So, like, if this bromine was initially on a wedge, then the oxygen attached on a dash here. But if we had the plus minus version, so if they were on a dash, then the oxygen would be adding on a wedge here. And we just have both options. So, again, it's kind of the thing of, like, you can think about this as long and for as much time as you have, but kind of the end of the day is if you form a stereocenter, you're going to get both mixtures. The only other thing to really consider is if you did syn or anti-stereochemistry, and when one of yours is not a stereocenter, you don't even have to show that. Because, like, there's no way that you can show the bromine and the O being added both on the wedges or dashes, because the wedge or dash on this carbon doesn't mean anything. It's not stereocenter. I know I kind of talked in circles. Questions on that? Where did the H go? Oh my gosh. Wow. Thank you. We have one more step. Beautiful. So last step, we just need something to come and deprotonate it. So I'm just going to take the Br minus from solution, coming and deprotonating it, giving us our final product. How could I have forgotten? That's bad chemical housekeeping over here. That's not better homes and gardens. That's worse homes and gardens. Okay. Could you explain why OH attacks in this case? So again, the Br minus could come and attack hypothetically, or the OH could come and attack hypothetically. And which one's faster? An intramolecular reaction is always going to be faster, just because the components reacting are trapped in a smaller area together. Yeah. Okay. Ding dong. Okay. So that is our halogen anti-additions. And with that, I am going to move on. I'm going to kind of move somewhat quickly for the next little section. Mostly just because in terms of our alkene families, these are the only two families where you really need to know the mechanism and where there's theory involved in the mechanism. The other alkene reactions I'm going to call complex alkene additions. And these complex alkene additions, we really only want you to know the line reaction. We are not, I don't think that you are required to know any mechanism steps for any of these reactions. And so we can do a lot of those pretty quickly because of that. So to start off, we have ozonolysis, a classic. So ozonolysis, I typically talk about as like being auction scissors. So they are scissors that come along and they cut open this alkene, this carbon-carbon double bond. And on one side, or on either side of that double bond, we put a carbonyl. So this, if we stop right here, we've cut open the double bond, we put a carbonyl on each side of the carbon. This is what we call a reductive product of ozonolysis. So ozonolysis, we have kind of two versions that we can do depending on our step 2 here. Both of them start out with ozone, O3. But then if we do it in DMS, dimethyl sulfide, which is also Me2S, 2 methyls and a sulfur, then it will stop right here and we are done, and that is our product. However, if our second step is hydrogen peroxide, H2O2, this is our oxidative conditions. And so it's going to go one step further. And if one of these or both of these are aldehydes, it is going to take any aldehydes all the way to a carboxylic acid. So it's going to add another oxygen here. And really, again, we're not teaching the mechanism of it because it's a little bit much. We just want you to be able to do this disconnection and draw the products, especially because it's very powerful for making reaction schemes. It's a great way to bust a molecule apart, which you don't know a ton of reactions that bust molecules apart. So to do this, what I'm going to do is I'm going to do this kind of fake mechanism each time. So I'm going to take my alkene and I'm going to cut it down the middle. And then I'm going to do the reductive conditions first because that's the easier one. So I'm going to take the 2 carbons that were in that double bond and put a carbonyl on them. And that's going to be the product of our reductive conditions. For our oxidative conditions, what we do is we are going to have the same thing, but if any of them were aldehydes, we're going to add an O and make it a carboxylic acid. Not too bad. Okay. For the second example, actually, I'm going to let you try examples 2 and 3. I'm going to give you like all of 90 seconds. So, So, for these, one thing to notice for this middle example is when we have a benzene ring, also called an aromatic ring, does not do alkene additions. So, because these double bonds are conjugated together, there are p orbitals on all of the atoms, and they have a lot of resonance between them, they are going to behave very differently than an isolated alkene. And we're going to learn the differences of that in Lecture 9 on Thursday. So that is coming. But the only one that we are going to split for ozonolysis is this bottom one. So our reductive conditions, we have a ketone and we have an aldehyde. And then for our oxidative conditions, we just need to make sure that aldehyde is turned into a carboxylic acid. Lastly, for the bottom, when we split it, in both cases, when we split it, if we just did the reductive conditions, we get 2 ketones. And so because both of these are ketones, there's not an aldehyde that if we were in oxidative conditions would go further to a carboxylic acid. And so both the oxidative and reductive conditions are going to have the same product here. So that's the extent of what you need to do with ozonolysis. It's very powerful. If y'all were doing like big syntheses, this would be like a major strategy. But no synthesis for E-17. So no aldehyde equals no OH. But if there are 2 aldehydes, 2 OHs. That is totally correct. Yes. So like if this was an H, then we would have H in this version on the bottom, and then we would have another OH up top over here. Yeah.
We don't need to say like 2 equivalents of hydrogen peroxide or anything like that.
Nah. Like, I mean, we're not even telling you the mechanism. So like, yeah. Some classes are very strict with equivalence of things. We are not. Okay, I'm going to move on rapid fire and just briefly touch on these. So we have osmium tetroxide, which actually, now that I'm looking at it, I feel like Serenia might have used a different reagent for step 2, or she might have just used 1 overall. And so apologies if that is off. That would be one thing to just check with lecture notes. But the whole purpose of this reaction is to make a vicinal diol. So vicinal, we said 2 things in the same vicinity, or they're kind of neighbors to each other. Diol, 2 alcohols. And so specifically, this makes a syn vicinal diol. Another word for a divicinal diol, they're often called glycols. And that's kind of for biochemistry. So if we want to make a vicinal diol, we can use osmium. I literally think about how osmium, OSO4, has a lot of O's in it, so it adds 2 O's, not deeper. There's also going to be a way that we can make a vicinal diol with an anti-orientation here. So with osmium, we see that they're both added on wedges or both on dashes, so syn addition, and there's going to be a version where they add anti that are made from epoxides, so we'll see that later. Then we get to my favorite reagent in all of OChem 1, which is MCPBA, metachloroperoxybenzoic acid. She is an icon. She is a legend. She is a carboxylic acid that has a peroxide OO bond in it. She has a quirky 1-step mechanism with 4 arrows in the 1 step. I just think they're neat. Like, it is one of my favorite reactions. And so anytime you can use MCPBA, use it. What you get from using MCPBA with this big concerted mechanism is you form an epoxide. You have a 3-membered ring with an oxygen. Now this looks really, really similar to a 3-membered ring with a bromine, the cyclic bromonium, cyclic chloronium ion. And the thing to consider with this is they are going to be very reactive, like that intermediate. The only thing that's really majorly different here is it's a neutral formal charge, because oxygen, we know, likes 2 lone pairs, 2 bonds. So with this, epoxides can exist on their own, but we'll see more of their reactions in a little bit. So epoxide formation, MCPBA. Last one, what if we want to dissolve away an alkene and make an alkane? So to make an alkene into an alkane, the 2 things that we are adding are hydrogens. And this is also a syn addition in terms of our stereochemistry. yeah, again, because these were not expecting you to know any mechanisms, even this one, which I put the mechanism just because I think it's fierce, you aren't required to know the mechanism. So it's really just looking at the line reaction level and knowing these kind of three things that are added, or three questions for the alkene addition: the what, where, and how. So that is our complex alkene addition family. Any questions before we do a hard pivot? I'm going to try to use my transition music, but I don't think she'll come through loud. So let's see. So let's talk about the Wittig reaction. The Wittig reaction is going to be the third and final way that you will learn in Chem E-17 to form an alkene. It takes an aldehyde or a ketone and this new functional group that's called an ylide, where we have a negative charge on carbon right next to a positive charge, in this case on phosphorus. So this is called a phosphorus ylide. Ylide is just this kind of charge separation at adjacent atoms. And it is going to create an alkene, and specifically it creates a Z alkene or a cis alkene. That's kind of uncommon. Remember, we said that for E2 and E1, we typically favor the trans internal alkenes. So this Wittig is really helpful to make this Wittig is really helpful to make alkenes that are hard to make via E1 and E2. So in addition to forming these cis alkenes, which are less common with E1 and E2, it's also very easy with the Wittig reaction to make terminal alkenes. So if you ever need to make a terminal alkene, you can either do it by having a 1-carbon aldehyde or ketone. I guess it has to be aldehyde if it's 1 carbon. Or you can have a 1-carbon ylide over here. And that's going to make your double bond with 1 carbon on one side. Terminal alkene. So with this, let's kind of unpack the components of it. So first off, ylide formation. We make ylides from alkyl halides in a 2-step process. The first process is PPH3. That phosphorus has a lone pair on it and is going to go and do an SN2 backside attack on the alkyl halide. And then, once we've installed our PPH3, she now has a positive formal charge, but that's okay. Like, we're trying to form the ylide, which has the positive formal charge. And remember, phosphorus is just below nitrogen on the periodic table, so it would be kind of like an NH3 attacking, and then you have nitrogen having 4 bonds, positive charge. So that's kind of formal charge, keeping track of it. And then we call it N-butyl lithium. It's really just an alkyl lithium, which is acting as a strong base. The strong base is going to deprotonate right here at the alpha position to the phosphorus, and that is what gives us our negative charge on the carbon, and we have this ylide. So a couple things to notice. One, when we form our ylides, we have an SN2 attack happening. And so because of that, we typically want our alkyl halides to be primary or secondary for forming an ylide. We aren't really going to be able to make an ylide with a tertiary carbon there because of this SN2 attack. Okay, then once we have our ylide, we know that carbon nucleophiles are really, really strong and reactive, just like we saw the carbon nucleophiles in like a Grignard, like a MGBR. The carbon going and attacking. So the negative charge on the carbon is going to push up on the carbonyl. Then we've kind of joined this ylide section with the carbonyl section. And I know it feels kind of weird because phosphorus, we said, has 2 mini bonds, and so it has a positive charge. But the next step, we are going to make 1 more bond to it, and then suddenly it becomes neutral again. This is one of the quirks of phosphorus being further down in the periodic table and having an expanded octet. You don't really need to know a ton about it, but just clocking the formal charges that change. And this is like the fierce and iconic moment. When we do this little intramolecular reaction, we make a box, a little 4-membered ring. And so I always call the Wittig the boxy boy reaction. And it just feels very like aesthetic and very like if the Wittig reaction was a person, it would be one of the like Gen Zers who do the like chin scraping thing. I forget what it's called, but like they like the aesthetics. So once we are at our box, then we can do this cool kind of collapse that happens. So we need to make a carbon-carbon bond. And at the same time, we need to break this carbon-oxygen bond. And so we have this concerted reaction where truly the box just like collapses and then splits apart into two molecules. And it's just like, it's very satisfying. It's like, wow, okay, fierce queen, work. So that's the VIDIG. I'm not going to get too much into the details. You'll need to like write out the mechanism and practice it. It's a great type of exam mechanism. Mewing, that is what it's called. I do hate that. But if the VIDIG reaction was a person, they'd be out here mewing. They'd be making TikToks. They'd have a little following. They'd think that they're an influencer. But, okay. So with that in mind, let's do some synthetic disconnection practice. So I'm going to do the first one, and I'm going to have y'all try the other two. So here, for these two examples, we have an alkene, and we want to think about what the options were to make this alkene via VIDIG reaction. So what we are going to do is we are going to split the alkene, and on one side of it, we need to make it a carbonyl, and the other side of it, we need to make it an ylide. Now you might be like, Colton, which side do we make which? That's a great question. Both are potentially options. So I'm going to start off with the top one. This top one, we know that we have two hydrogens here, so that's a CH2 up top. So the CH2, we could have it be a carbonyl, or we could have it be an ylide. So we add the PPH3 and the plus and minus. So then, depending on what we do to the top one, the bottom one is going to be the opposite. So if we had the top one be a carbonyl, the bottom one, we now add the PPH3 plus and minus, and that's an ylide. And that's kind of option one. And option number two, we would have the bottom one be a carbonyl because the top was an ylide. So now that we have the potential options, which is a better route for making this alkane? Vote in the chat, option one or option two. Which is going to give us better yield and be the better VIDIG reaction? If we make the CH2 our carbonyl, or if we make it our ylide? Option one or option two? Y'all are too young to remember American Idol voting where you would vote on your phone. But I was just thinking, like, because it was so slow getting answers, I'm like, what if you just like voted multiple times to vote more for who you think wins? And we had little statistics, and then the winner. You could dictate chemistry with your votes, maybe. That's where my head goes because it is late, and it's late in the semester. The winner, in fact, not based on popular demand, but I think most of you were kind of right. There was a lot of thoughts. The actual one that happens is option two. And the reason goes back to the step of ylide formation. Remember we said ylides are going to be better if they are primary, and then after that secondary. Tertiary ylides won't even happen, but it's because of this SN2 attack. So think with that in mind, we are always going to form the ylide that's smaller. Like, this isn't even primary, this is methyl. This is like the fastest SN2 that could possibly happen coming from methylbromine. Versus this one, it's going to be a secondary SN2, which is just really slow. And so it could happen. Like, I don't think that we would dock full points on the exam. We might like dock a point or something. But we need to think about which one's going to be the better ylide. So with that in mind, take all of 90 seconds, 2 minutes. For this disconnection, draw the two versions and then figure out which one's going to be the better route because it has the less substituted ylide. And then for this one, try just drawing what the product is going to be of the VIDIG reaction. how'd you do? I didn't want to draw a whole benzene ring, so I just abbreviated it with pH. And then this carbon out here. There still is the hydrogen, but we don't need to draw it. Then over here, we literally just chop this off, glue this together to this, chop this off. It's kind of like if analysis was like disconnecting the Legos, Vidig is like reconnecting the Legos. And just like this, you can see how just alkenes alone could take up a 3-hour lecture. And in the version that we teach in the summer, there are actually like 8 more reactions. So like normally in the summer version for alkenes, I reveal my like ChemDraw magnum opus, which I will show you. My ChemDraw magnum opus is this, and it's the alkane reaction web. And it groups all the reactions into little families, and I have little boxes that zooms in on all the different ones, and it's like beautiful, and it's just like, ugh. And it's the background for the course. It's my favorite. But for y'all, because so many of them were cut, like, I thought about doing the wheel, but like, look at how much is cut. And I was like, yeah, I don't know. I don't think you need it. I think just the section notes version will be fine. But yeah, I said I can't butcher my baby, my alkene wheel. But with that in mind, I know that we are a little bit over time, and also I know that I normally go till 7:30. So with the last like 10 minutes, I'll do one more section here of this kind of alcohols leaving group situation. And then in the video afterwards, I'll do the final 2 sections on ether and epoxide. So again, apologies that it gets so drawn out, but I do think that it's a more meaningful engagement than if we just did a light touch on all of these and just kind of plowed through. So let me get a transition.
What it seems.
I don't know if any of that came through, but that was the Wizards of Waverly Place, the original, not this remake. Even though a friend of mine from Harvard was a writer on the remake of Wizards of Waverly Place, which is kind of a weird thing. But we have a problem. Alcohols are not good leaving groups. And sometimes we want to kick them out. We don't want any alcohol in here. So let's start off with a harebrained strategy. We could take our alcohols and dump them in a vat of acid. Like, I mean, it works. It'll get rid of the alcohol. Let's see how. So if we do it with a tertiary alcohol, we're in strong acid, we'd protonate it. And then we have a really good leaving group, OH2+, great leaving group now. Leaving group can just leave because it would form a tertiary carbocation. And then the bromine, Br- from HBr, would come in and attack. Bada bing, bada bang. We now have an alkyl halide, which is a good leaving group and can do a bunch of other things. Sure. Similarly, if we have a primary alcohol, then what we could do is we could protonate it, again in the first step. And then the bromine can come along and do an SN2 attack because OH2 is a good leaving group now. And then we have an alkyl halide. So we have a kind of version that works for SN1 and a version that works via SN2. But why is this strategy of throwing your molecule that you spent months and years and maybe your PhD and it's more precious than real living people to you, why might we not want to throw that in a vat of strong acid? Well, one, putting a molecule of interest in strong acid could lead to other functional groups on the molecule reacting. So it could do other things that you don't want it to do. Two, it's like very harsh reaction conditions. And so things can go wrong broadly. But then also, what if we had a secondary alcohol? Well, that's not going to be very good at SN1 or SN2. So we need some other strategies for making alcohols leave. So let's look at these reactions. So we have 3 different ways that we can make alcohols into much better leaving groups. And I guess the thing that's most important to pay attention to, the reason why we have choices here, is it's related to the stereochemistry on this carbon at the alcohol. So we have one version that's going to retain the stereochemistry. We are going to make it into a tosylate, which is a really good leaving group, and we keep the stereochemistry that we started with. And then we have 2 versions that are going to turn the OH into a halide, and it's going to invert the stereochemistry. So for this first option, what happens is you literally do this SN2 attack, which feels very weird because it's a sulfonyl and we have all these like SO double bonds and everything. But we kick that off. We have an intermediate where this is protonated, and then we just deprotonate it. And so why does that not change our stereochemistry? Well, did we attack this carbon at any point in that mechanism? No, we did not. This oxygen in the alcohol is this oxygen in the tosylate. And now suddenly it's a really great leaving group for doing SN2, SN, like any of the lecture 7 reactions, essentially, substitution and elimination. Over here, however, when we do it with like thionyl chloride, the mechanism's a little bit different. So it's going to do, again, kind of an SN2-like attack. You would get this intermediate here that you would deprotonate. And then the final step, and I've only drawn kind of like critical steps here. Really kind of cool. What happens is the chlorine that you kick off in the first step comes back around. This folds up and creates another double bond on the sulfur and kicks off the chlorine. And what you get that comes out is an SO2 gas. And anytime you can form a gas in a reaction that's going to bubble out of solution, it's going to drive the reaction forward both thermodynamically and also by Le Chatelier's principle, because the gas is literally leaving the reaction beaker. And so you aren't going to get a buildup of concentration of the gas. So it's really, really favorable in making this really excellent SO2 leaving group. But at the end of the day, what happened was we have replaced our OH with a Cl, and we have this key SN2 step at that carbon. Similarly over here for PBr3, we are going to have a step where a bromine comes and attacks, and we don't have as good of an explanation for you as why this is an excellent leaving group, but it is an excellent leaving group. This phosphorus with 2 bromines and an OH. To be so honest, I don't know a ton about phosphorus chemistry, and so I've just taken the professor's word that's a good leaving group. So with this, these 2 versions, we invert the stereochemistry. The top version, we don't. So when we start to work problems, that's something that we need to keep in mind. So let's look at this top one, and note that I've changed this a little bit from the version that appears in the section handout, so I'm going to be doing it based on mine here. So every time we are doing a step in a reaction scheme, we need to ask, did an SN2 happen? So over here, we have SOCl2, and SOCl2, if we're making alcohols leave, we see that this is an SN2 step. And so we need to invert our stereochemistry where the OH was. So that is going to replace our OH now with a Cl, and we've inverted our stereochemistry from a wedge to a dash. Okay. Well, then we have KCN. What is that going to do? Well, we know that this is Cn minus. The K is just covering up a negative charge. And suddenly we are in alkyl halide with some nucleophile or base. We need to be thinking about SN2, E2, and SN1, E1 GFP ranking. So for SN2, it's going to be fair because this is secondary. For E2, it's going to be fair because it's a moderate base strength between OH minus and H2O. And then for primary, it's going to be fair. So if they're all tied, who wins? SN2 does, because it's faster. And so we are going to have another SN2 step that inverts our stereochemistry here. And our final product that we get out of it is we are going to be adding a Cn. And the Cn is going to be on a wedge. So, if we did one inversion, it became a dash. And if we did a second inversion, it went back to a wedge. It's kind of like turning a light switch off and then back on again. It returns to the original condition. And so we say that when we have double inversion, it is the same as retention over here. And again, I don't know if the music will work, but we've stumbled across a wild synthesis strategy. Oh my goodness. So, depending on if we want to add our nucleophile in a way that appears to be retained stereochemistry or inverted stereochemistry, that tells us which we need to choose of our making our alcohol into a good leaving group. So if we want it overall to appear like a retention of stereochemistry, we need to make sure we have two SN2 steps. So we need to use PBr or SOCl3 to make our alcohol leaving group, and then we have whatever our nucleophile we want to add come on. If overall we want inversion of stereochemistry, then we only want the SN2 to happen when our desired nucleophile attacks. And so we want to use tosylation, this first option, which retains stereochemistry in that first step. So overall, in this scheme, there is only one SN2 step. First, this one has two SN2 steps, and so we can get the different stereochemistry. With that, I do think I am out of time here, so I will do the rest of these as well as the last two sections in the section video for a little bit later. But thank you for coming by. I hope that what we did cover was helpful, and I'll stick around for some quick questions for like related to section, and then I'll take like a 5-minute break, and then I'll do office hours questions. So, well, hello there. It's just you and me now. We are in here. We are going to finish off section. So let me get this back on. So we had just talked about this kind of synthesis strategy of doing two SN2s, and overall it's a double inversion, which is a retention, or doing one SN2 and it's overall an inversion. So let's look at this. If we're going from this to this, overall we've done an inversion. So how many SN2s need to have happened? Only one SN2. So we know that we need to make this into a leaving group over here where we are still on a wedge. We do a retention. So the reaction that we want to use to make this OH into a better leaving group that retains stereochemistry is we want to use tosylation. Okay, well now we are at our good leaving group formed, our OTS, and we need to install an N3. And so we want to use N3 minus, and we just cover up that minus with a cation. So NaN3 is our nucleophile. So this one did not involve an SN2. We did not react at this carbon at all. This one is an SN2, so we did inversion. Last one down here. Overall, we want to do a retention of stereochemistry, which means we want both of our steps to be SN2s. And I think I changed this one from the one that's on the section handout, so just heads up. So, firstly, if we want to do an SN2 and make this into a better leaving group, we can either use the bromine or the chlorine, so we can do PBr3, or we can do SOCl2 and pyridine. I'm just going to use PBr3 just because. So this makes our bromine. We're on a wedge now because we inverted. And then we want to do an SN2 to install an SH. So we want SH minus as our nucleophile. We cover up that negative charge with a cation. So we use NaSH. So that's making alcohols leave. Up next, we have ethers. So this is very much a me thing. This is not an everyone thing. This is not an IUPAC nomenclature thing. But I like to talk about ethers as having an anatomy, kind of like a classification like we had for like we had for alkyl halides and alcohols of primary, secondary, tertiary. So what I would do is I look at both the carbons on either side of the alcohol, and I see, okay, on this side it's primary, on the other side it's secondary. Touch two carbons, touch to one carbon. So I would call this a 1' plus 2' ether. I'd call this one a 3' plus 2' ether. This one a 1' plus 3' ether, and this a 2' plus 2' ether. So all of them are ethers, but this is going to be a handy way of thinking about ethers as we go into thinking about how to build ethers. So building ethers, there are two main reactions that we do. And the number one thing that you should think about when you're asked to make an ether is this first option, the Williamson ether synthesis. So the Williamson ether synthesis can make a 1' plus any prime ether. And any prime meaning the other side could be primary, secondary, or tertiary. The only real requirement is one side of it needs to be primary. So the way it works is you start out with your any prime alcohol and you add NaH, which adds as a base. So it makes it O-. And then if we have a primary alkyl halide, this will do an SN2 attack. And that will make our ether. Done. Why does this have to be a primary alkyl halide? Because if it was secondary, then it would be fair for SN2, and it would be good for E2 because we have an O-, an alkoxide. So in order to get actually our SN2 as the major product, we need this to be a primary alkyl halide, because then SN2 versus E2 would be good, good, and SN2 predominates because it's kinetically faster. Okay, so then my question is, which of these ethers could we have made via the Williamson ether synthesis? Well, we could have made any ether that has primary as one side. So we could have made this one, or we could have made this one. These we could have not made via Williamson ether because you don't have primary on one side. So the other way of making an ether, this way was primarily SN2, right? We had this SN2 attack here. The other way to make ethers is an SN1 route, and the requirement for the SN1 route is one of the sides has to be tertiary. So essentially what you do is you add your two alcohols and acid. In your acid, you would protonate the tertiary alcohol, and then the leaving group would leave, and it would make a carbocation. Then your other alcohol would come in and attack, and then you would do a deprotonation. Bada bing, bada bang. So it's really just an SN1 route. Like a lot of these families of reactions, I just call fancy substitution elimination. It's substitution elimination with strings. Now we have new functional groups, but we're still just doing SN1 and SN2 at the end of the day. So which of these could have been made from the ether synthesis and acid? Well, any of them that have a tertiary side. So one thing that you'll notice is this one, we did not actually make via SN2 or SN1 easily, and it's because it's secondary. Secondary ethers are really hard to form because they're fair for both SN1 and SN2. And so we might turn to other methods of making ethers. So we can also make ethers from an alkene, either the halo, the anti-addition in alcohol solvent, or alcohol addition. Or we can make it from an epoxide, which we'll talk about in a second. Another thing is we can make cyclic ethers by having the alcohol and alkyl halide be on the same molecule, like this. Cool. So that's how to build an ether. So let's look at the first two kind of practice down here. So what we just said for this one, it's not going to be great to make via SN2 or SN1 because it's secondary on either side. So maybe the way to make this is to think about doing this from an alkene. So from an alkene, what we could have done is we could just split one side, and we can make one side of it the alkene, and the other side an alcohol. And we do this with an H+ catalyst. So that would form this carbocation in the first step. Like this would go and grab a hydrogen. And then this would come in and attack, and you would deprotonate. So that's probably going to be the best way of making this ether. And really the only way that we could get this in a reasonable yield is because it's symmetric. It looks the same on both sides. Now this ether we see is primary and secondary. So because we have primary, I'm thinking Williamson ether synthesis. So we want this primary side to be the side that was an alkyl halide, which means this other side was the alcohol. So we can disconnect and do these. And remember, our steps are, we do 1, NaH added to our alcohol, and then 2, attacking our alkyl halide. Cool. Then let's move on and talk about epoxides. Dramatic girlies. Normally I have like a pair of like little sunglasses. I'm like, do I still have it in here from the summer? I don't think so. Pause. I should pause the video as I'm scrolling. But no, I don't see it. Oh, no, there it is. Cool functional group. Epoxides are reactive. They like to explode. An epoxide is a 3-membered cyclic ether. At this point, you've identified epoxides before on the exams. Very strained, much react, many explode. IUPAC-wise, it's sometimes called an oxyrain, which gives it like an old mythical energy to it. Epoxides, we've already seen one way of making it with MCPBA, my favorite way. But we can also make epoxides from a halohydrin, which halohydrins we said that we could have made from an alkene with Br2 and H2O. So there's kind of a roundabout way, a 2-step way of making epoxides from an alkene, or a 1-step way of making an epoxide from an alkene. So I do this with NaOH. I think Serenia used NaH. So either one of these work. And basically what the reaction does is, first step, you deprotonate the O in the alcohol. And then you have a negative charge next to this bromine. It's just going to do a reach around SN2 attack and kick off the bromine. And that makes our cyclic ether here, our epoxide. Remember, halohydrin, halogen, and alcohol that are neighbors by 1 carbon. So making epoxides is actually pretty easy. The thing that's a little bit more involved is epoxide opening. So when we have an epoxide where there are different substitutions on each side, tertiary versus secondary, then the question kind of becomes, okay, we know a nucleophile is going to attack, but is it going to attack on the tertiary side or is it attacking on the secondary side? Well, when we had the cyclopromonium, we said that this was always going to attack on the more substituted side. But for an epoxide, we can actually control which side it attacks on, based on whether we do it in acidic conditions or basic conditions. So if we do it in acidic conditions, the first step is we protonate the epoxide, and then suddenly it's behaving exactly like that cyclic bromonium ion. So here, with the cyclic bromonium ion, the thing that's going to matter most is the partial positive stabilization. And so the more stable partial positives on this tertiary carbon, and so our nucleophile is going to go and attack this tertiary carbon. So in both of these versions, where if we did H3O plus or alcohol and acid catalyst, our nucleophile from this step is added on the more substituted carbon. Now, if we did it in base, the primary thing that controls which side reacts is really kinetics. So it is just simply faster if we have some sort of base, like an OR minus, to go and attack the less substituted side. Yeah, it's because we have a high energy donor that can just go in and attack. And we don't have a partial positive, or we do have a partial positive charge, but we don't have quite as dramatic of a partial positive charge because we don't have that plus on the oxygen really exacerbating the dipole. So we could have OR minus come and attack, and then we add our OR nucleophile on the less substituted side here, since we were in base. Or another thing that we could have is we can have a Grignard come and attack on the less substituted side. Now, in all of the cases here, this acid versus base controls the regiochemistry of, does our nucleophile add on the more substituted side or does it add on the less substituted side? But the stereochemistry for all epoxide openings is anti. So since our epoxide here was on a wedge like this, we know that the nucleophile has to attack from below. It will either attack the top carbon or the bottom carbon in terms of the tertiary or secondary carbon, but in both cases, the approach for the molecule is from below because that is where our antibonding orbital is. So what we see is no matter which carbon our nucleophile added at, in all cases it added on a dash because our original epoxide was on a wedge. So over here, the oxygen that was in this epoxide on a wedge becomes the OH, and we see that no matter which side it goes to, it stays on a wedge. Okay. So, oh, and that I guess brings me to my favorite, like, epoxide meme that I've typeset. I didn't make it, but we are opening an epoxide. We're cracking open an epoxide. If we call the epoxide a cold one, and the thing that we are opening it with is the boys, we are cracking open a cold one with the boys. Hey. Feel free to leave feedback if you didn't like that joke, or if you did, let me know. Oh, I also typeset this. This is the idea of double inversion versus retention. You'll see it in Chem 27 involving sugars. Yeah. But finishing this off. So let's look at this practice now. So the classic thing that you're looking for with epoxides, and it's epoxides and alkenes. If you are like trying to touch the earth and be like, something happened here, you know that an epoxide or an alkene took place if you have functional groups on adjacent carbons. So with an epoxide, you know you have functional groups on adjacent carbons because one of them is always going to be the OH from the epoxide, the other one's going to be the nucleophile. With an alkene, you know you add two things to the neighboring carbons that were in the double bond. So that is what we're looking for. And here we are told that this first molecule comes from 2 3-carbon molecules. So I might think about trying to disconnect it here, right? Like a 3-carbon, 3-carbon. So it's kind of weird because we don't really think of this as a functional group, right? This is kind of an R group, and this is an OH. And we don't have any alkene reactions that add an R, like an alkyl group. But we have an R and an OH adjacent to each other for Grignard addition to an epoxide. So we need to make one side of this an epoxide. So I'm going to make it an epoxide like this. We don't need to worry about stereochemistry because this molecule at least doesn't have a stereocenter. That's a lie. That's a bold-faced lie. We don't have to worry about stereochemistry because I didn't indicate it here in the product. Yeah. So imagine this was here and we have plus minus a mixture. Then we would start off with the version of this plus minus is a mixture. Okay, and then the nucleophile that we would add is a 3-carbon Grignard. So we have first step our Grignard in ether, and second step we do an acid workup. Cool. So that adds our R and our OH adjacent. Over here we see that we have an OR and an OH that are adjacent to each other. I don't know any alkene reactions that do that, so we're in kind of epoxide land. And actually, maybe before we go on to this one, I'll check one last thing over here. We know that Grignards are basic. Did this Grignard add to the less substituted side to get this product? Yes, it did. So just a confirmation to make sure that our epoxide opening conditions are met. So here, we know we want this to come from an epoxide. So let me just make an epoxide here. And again, they don't give stereochemistry in the product, so I'm going to say that we can ignore it. And now the question is, the thing that's added is this OME. So we know we want an HOME. But the question is, do we want to add it an alcohol in base or acid? So do we want this to be HOME H+, or do we want this to be NaOMe? And to answer that, we have to look, okay, do we want it to attack the more or the less substituted side of the alkene? Here, we want it to attack the more substituted side of the alkene, And so the way that we can get an alcohol to attack the more substituted side for an epoxide is to do it in an acid. And then that is going to add our OMe on the more substituted side. It's kind of comparing and contrasting these two strategies. In both cases, you get an ether and an alcohol that are neighbors to each other. But in one of them, the OR is added to the more substituted side, and the other one, it's added to the less substituted side. Cool. Last thing to finish this off, practice number 5. So, bloop. Weird time. So, there are a few things that are kind of unexpected. So, one, if we just look at this, it looks like we've substituted a Cl for an OH, right? So, the thing that you might be thinking is do an H2O attack, and then we have this, and then positive charge, and then you deprotonate it. But the issue with this route is stereochemistry. We know that if we do an SN2 attack, we're going to invert the stereochemistry, and suddenly this is going to be on a dash if we draw our OH over here. And so, overall, we know that we have retained stereochemistry. We've retained it as a wedge. And we know we did a substitution. So that tells us that we did 2 SN2 steps. So it's kind of like what we saw over here. Like, overall, we retained stereochemistry, but we did substitution, so we must have done 2 SN2 steps. So, I mean, one of our SN2s has to be this OH attacking, right? What's the only other thing that could attack? Well, it's our sulfur. So let me color this. So, our sulfur here could do an SN2 attack and kick off the chlorine. And if we do that, what we get is this kind of thioepoxide. And that would make, I'm going to put this down on a wedge. And it's because, remember, when we do our SN2, there are kind of 2 ways we can do it. One way is we can draw our new nucleophile in the same spot and then change it to a dash for the dash and wedge. The other thing that we could do is we could draw the nucleophile from behind and then keep the wedge and dash and just make it down instead of up. So because we're forming a 3-membered ring, I need to preserve the sanctity of that geometrically to kind of keep the sulfur there. So it's going to make this go from being on a wedge up to being on a wedge down. But our stereochemistry has inverted. If you do the RNS here, this is priority 1, priority 4, 3, and 2. This one is R, whereas over here we have priority 1, 4, 3, and 2. 1, 2, 3. This is S. So we did change our stereochemistry. We did do an inversion. Then from here, this is where H2O can come in and attack. And this, again, is kind of really like reminiscent of an epoxide with a plus. So that would be acidic conditions. And so we're attacking the more substituted side. So that really agrees with what we saw with epoxides in acidic conditions. And it's really this positive charge, like the cyclic bromonium. That means we're going to attack this more substituted side. So then that's going to get us with OH2, like this. And now we should be back over here. And again, this is the one where I attacked from the other side, so I kept my wedge a wedge. But really, this flipped our stereochemistry all the way back to what it was before of 1, 2, 3, it's R again. So we went from R to S to R, inversion, inversion, double inversion is just retention. Last step, another equivalent of water is going to come and deprotonate this, make it neutral. So This is also very similar to a question on PSET 7 that I was talking about with a student in office hours. Let me see if I can find it really quick. I simply don't want to. Is it open? Oh, it's open. Yeah, this is very similar to question 5 on PSET 7, where there's a double inversion is retention. But I think that that's all I have for you for now. Thank you for watching the section video, even with it being quite long. If you have any questions, feel free to reach out. And again, if you are not in my formal section but would like to meet with me with a mid-semester meeting, just send me an email and I will send you a link. Thank you. Have a good night.